That's also a great plus. Our current openings are also looking for full stack engineers, UI developers, cloud architects, strat modelers, among other things. And I'm going to put a link in the chat to take you to a full list of all of the roles that we have available right now, as well as the email addresses for two of our human capital management, our people in charge of recruiting. Their names are Anna and Savannah. So if you have any additional questions about the roles, they're going to be the people to get in contact with. I know that we mentioned this a little bit earlier, but we do have some swag to give away as well. At the end of the event tonight, we'll be giving away a really soft hoodie, which you can see Soraya is wearing, very comfortable, as well as a small portable Bluetooth speaker / phone charger. So as I mentioned, I'll be putting those links in the chat for you guys to take a look at. Soraya and I are, of course, also happy to answer questions tonight. But yeah, we're excited to hear from James. So thanks for having us.
Yeah, and feel free to reach out on LinkedIn too to either one of us if you have questions.
Yes.
Thank you.
All right, very good. So let's get James up here. James, you should be on the screen now as well, and I will take Soraya and Madeline off. Thank you both for being here to help us out. Appreciate it.
Okay. Thank you very much. Yeah, I wish that I could earn that swag, because I got to tell you, this Goldman T-shirt, you know, it's worth it to come work for us just to get the soft hoodie and the T-shirt. It's a softness you'll never know otherwise. So let me see here how I share my screen. We want to share this one. Okay. All right. All right. Let me just make sure that we have this up. No technology issues. Yep, everybody can see. All right. Well, thanks everybody for coming tonight. I'm James Barwick. I work as a software engineer at Goldman Sachs in the electronic trading division. I work on a team that specifically focuses on mitigating trading risks. We have dozens of risk control implementations. They do things like limiting order rates, checking customer credit, checking market impact of order flow. And, you know, trading systems are often latency sensitive. So when I tell people that I work on a Java-based trading system, they're pretty intrigued. So I thought that this would make an interesting UJUG talk. So, you know, the field that we work in is vast, and all of our jobs and interests take us down different paths of learning. So my intent tonight is to share with you what I've learned on my journey as an engineer. And I'm hoping that each one of you can leave this talk tonight with a piece of knowledge or perspective that can help you improve as an engineer. I'm hoping that every person feels like there's at least one juicy tidbit that's making their attendance worth it. While this isn't a deep dive into performance profiling tools or how the JVM works, we are going to touch on some of those things. We're just not going to go terribly deep. Rather, we're going to focus on a breadth of concepts that are easily digestible and hopefully practical for the majority of the developers. I can't give any specifics about the latencies or the low latency technologies that I've used with my employers. So I've picked out a couple quotes from the internet to demonstrate the criticality of latency in trading. The first quote should give you a general idea of the latencies that we work with. Microseconds is usually the unit of measure for most trading companies. Not all trading strategies are speed dependent, but some are very speed dependent. A pure price arbitrage strategy would be the primary example of a speed dependent strategy. If you're not familiar with a price arbitrage, that would be like if a security is traded on two different exchanges and the price is slightly different, you could buy one, sell the other to snatch up profits from that inefficiency. But you know, that strategy isn't unique. So if you aren't the fastest, you're out of business. And you know, generally these days, those inefficiencies in the market have been reduced to almost nothing. So the second quote here shows just how far some players are willing to go to get a slight speed edge. So microwaves are an alternative to fiber optic cable for transmitting data. It's slightly faster than fiber optic, and it can cost many millions to set one of these networks up just for that slight speed edge. So for some ultra low latency HFTs, they may find going to that extreme worth it if they feel like their competitors are going after similar opportunities that they are, or that they're getting their trade signals from the same market events. So the Java trading system that my team works with, it doesn't really go to those extremes, but we are still very mindful of speed. It's meant to be a feature-rich trading system that can accommodate a wide variety of clients, but I would still consider it low latency. GS clients use GS for a variety of different use cases. One would be the simplest use case, just purely exchange connectivity. But we also offer a smart order router. So clients can send an order and we figure out the best market to send it to. And to get even more advanced than that, we have algorithms that clients can utilize to, say, trade a certain number of shares throughout the day with a targeted weighted average price. So that way the algo just kind of works the order over the day. Like maybe your grandma left you a 10,000 block shares of Apple, and you want to sell out of them. You could have GS work that order for you throughout the day. The trading system also has a lot of control limits that can be finely tuned to protect the client GS as well as the exchanges. The level of risk control that we offer would be very expensive for clients to build in-house. The Java-based trading system, it's not ultra low latency, but there is still a high emphasis on speed. So as a developer, my contribution to building a low latency system is being mindful of performance in my day-to-day job when I'm writing code and things like that. A lot of people, when they're writing code, they don't consider performance. They use premature optimization as justification and not think about performance until there's a performance problem. And in my opinion, that's not exactly what's meant by the term. So I took some time to look into the origins of the term and the popular quote, premature optimization is the root of all evil. There's a lot of conflicting information out there about who the original author is and the first time that it was used. But I came across a passage that for me really hit the nail on the head. I thought it also paired well with another quote that I enjoyed from the same author. So for me, premature optimization means sacrificing a developer's time or the code's readability or maintainability for a performance gain when it isn't justified. Code should be written in a way that you or somebody else can come back to it years later and immediately understand what it's doing and be able to work with it without a lot of painstaking efforts. The readability, maintainability sacrifice is really only justified if the performance gain provides some kind of material business impact. In our trading systems, if we can improve the latency and the critical path for placing orders, we're generally going to do that if we're shaving off a tangible amount of time. For other operations like reading a start of day reference data faster, that really doesn't benefit us or our clients. So it's not something that we're going to put in time to optimize. From the beginning, you should seek to qualify and quantify the performance goals of your system. Consider performance when you're designing your architecture down to the data types when you write your code day to day. While that might seem like a lot of extra effort, I assure you that once you get into it, it really won't be. And it could save you from a lot of very time-consuming investigations and rewrites down the road. Bad performance is usually death by 1,000 cuts. So being mindful of the little things that could chip away at performance over time is really going to save you some trouble in the long run. Good performance starts with a good architecture. So I wanted to present this design pattern that I've I've seen used at exchanges for their order matching engines and for a variety of other usages. Looking at it, we can pick out 3 design patterns that it's made up, that it's comprised of. The first is the message bus communication pattern. The second is the CQRS pattern, or the command query responsibility segregation pattern. And the third is the event sourcing pattern. The message buses are sending multicast messages between the applications for communication. Multicast is a networking protocol that's faster than TCP and better at scaling and promoting fairness. While multicast performance isn't affected by the number of publishers and subscribers, all applications will receive the messages with about the same latency, as opposed to like round robining over TCP connections, where you're giving an unfair advantage to the first application and a disadvantage to the last application. Applications write to the performance bus, which is then read by a single application that's either going to reject or accept the command, and then add it to a sequenced event stream for all the applications to read from. Having all the apps see the events in the same order is useful for consistency, as well as troubleshooting. And if you're persisting the events on the event stream, you could even replay those events in the future if you want to troubleshoot a bug or test out a new feature under prod-like conditions. Communicating in events is usually more efficient than communicating in state, because a small event can have far-reaching impacts to state. So this keeps our messages between applications small, and each application can decide how that event should impact its own state internally. This architecture also offers some performance compromises. Namely, inter-process communication isn't free, particularly in a distributed system. So, anytime that you're crossing the PCI bus and making a network hop to another machine, you're paying a performance penalty. But that penalty is minimized if the number of applications in your critical path is kept to a minimum. So, ideally, the things that are important to your system are just taking a few hops from application to application, and every other ancillary piece of your system, it can be a little chatty if it needs to be. Performance aside, this architecture offers loose coupling, scalability, high availability, and determinism. Architectures aren't one size fits all, but I really thought this is a great example of how being forward thinking about a system's goals, and then bringing together some simple design concepts to make it happen. So once we get into the code, it may seem obvious, but one of the biggest things that you can do to avoid a performance issue is considering the complexity of your algorithms. Algorithms that traverse large data structures can really make or break performance. So a few tips when it comes to algorithms: get familiar with common design patterns. It's going to make life easier in identifying optimal algorithms for your use case. Choose data structures that have the most favorable big O time for the common operations that you're going to perform. So if you're going to be doing a lot of inserting into the middle of a list, consider a linked list as opposed to an array list. Consider how to get costly operations out of the critical path of your application. For our trading system, as an example, we have some risk limits that have some fairly complex keys. And in one case, the limit key is comprised of 5 different enum fields, and each of those fields can be wildcarded. So, the naive implementation would be storing and looking up these limits in a 5-dimensional hash map with some logic to handle the wildcards, where you would be, doing multiple hash map lookups. And that would just be slow and unwieldy code. So, we solve this problem by doing some pre-processing at the beginning of the day to expand those wildcards and build a data structure that has only one dimension. So while setting the limit set up can be a slow operation, that's not in the critical path for our trading system. And we've optimized the limit lookups that are in the critical path when we're placing orders. Here's another industry example of how the structure of your data that you're working with can put some fairly severe limitations on how fast of an algorithm that you can write. Fix is one of the first protocols used in electronic trading, and there's still some usages today, but most exchanges have moved on to faster protocols. So looking at the picture in the slide, there's a tabular representation of this message, and then up at the top you can see the message in raw form that you would get if your application was subscribed to these messages. So looking at the message, we can pick out a few issues with the protocol. The first and foremost, the tags can come in any order. So if you're interested in maybe only a couple fields from this message, or say you're only interested in processing the message if it's for a particular ticker symbol, then you're going to have to read through the message until you find the field for ticker symbol. If it's not the first field, then you're going to have to read to the next delimiter, read that tag. If that's not it, read to the next delimiter, and rinse and repeat. So it's a lot of wasted effort or time reading through that message. As opposed to the way that a lot of modern protocols handle this, where they give you a more structured format where the messages are at certain byte offsets. So ticker might just be at the fourth byte, and you can jump straight to it. So the exchange will give you a protocol spec definitions, and you can read through those messages, and there doesn't have to be any tags. There's no delimiters. All that's left in the message is the values. So you've reduced the size of the message significantly, as well as being able to access the elements that you want much quicker. So another benefit of that message being small is that it's faster to serialize, it's faster to deserialize. It can generally fit in one frame on the network, so you don't have to worry about fragmentation. So lots of good benefits there. Another issue with the fixed messages is that they tend to use a lot of ASCII values, and the way that's been addressed in exchanges have addressed this is by providing reference data at the beginning of the day. So they'll give you some maps of an integer value to a ticker symbol as an example, and that way your trading system can just speak in integer values throughout the course of the day, rather than using strings, which is a lot more costly of an operation. Sometimes I find myself wanting some empirical evidence that I'm using the best algorithm for something I'm working on. But performance testing, it can be time consuming and painful, particularly if you can't do it on your own box. So the micro benchmarking tool is great for testing little bits of functionality. So I recently used the micro benchmarking tool to test out a few implementations that I wrote for a rate control that uses multiple sliding windows. So it was just kind of some question marks in my mind about how moving data between those multiple windows would behave. And this screenshot is kind of meant to show you what I think is the minimal viable product for setting up one of these tests. So let me go through some of these details that I hope will help you successfully use micro benchmarking if you haven't used it before. So the warm-up iterations, this may seem like a small detail, but code performs suboptimally the first time that it's called. And after it's executed a number of times, the JVM, the OS, and the CPU, they've all figured out all these small runtime optimizations to make it faster. So you want to warm up that hot path before you start measuring. The measurement iterations, the more measurement iterations that you have, the more data points that you're going to have. So outliers are going to affect your result set less. And actually, each iteration consists of running the benchmark tests as many times as possible within a set window. So even if you're just doing like 3 measurements, you're really running the test function maybe tens of thousands of times. The state class is used to encapsulate everything that you need for this test. This prevents the compiler from recognizing optimizations like eliminating dead code and constant folding. Constant folding is when you have maybe in your test you have a function where you're passing the same inputs in every time, and the same result is being returned from the function every time. A function without side effects. In this case, the compiler might recognize that and decide it's going to optimize it by just storing the constant rather than actually calling the function. So the state class kind of prevents those optimizations from happening. Else, your test winds up running nothing. And likewise, with the benchmark test function itself, you want to return some value from that test to make sure there's no dead code optimization of that results in the test body being empty. So here's some sample results from a benchmark test. You get some latency percentiles in nanoseconds. There's some, you can tune the way that the way that you want to see the results, but this is generally what I've chosen to go with. So you get some latency percentiles, which I think that those are fantastic to have the percentiles like that. You also get to see the number of times that the test function was actually executed under the count column, and you'll see the variance of the distribution in the error column. So you'll notice here that I ran 2 tests, the do something function and the do nothing function. So the aptly named do nothing test is a test with an empty message body. I'm in charge of naming functions on our team, by the way, because I obviously just have a knack for it. I don't know, these test function names just come to me. So the do nothing test has an empty test body, and its purpose is to kind of act as a baseline or a control for your experiment. So if any other of your other tests perform as well as this baseline, it's a sign that the JVM may have optimized out some of your code. And in that case, you're going to want to go back and double check that you've encapsulated everything properly in the state object. The latencies in the benchmark tests are best used as relative comparisons. They aren't, indicative of performance at runtime. You're running on different hardware. You're avoiding garbage collection for the most part. Your memory layout is going to be different, and in an actual application, you're likely dirtying the cache a lot more. Whereas in one of these tests, you're running the same function over and over. If all the same objects are being used, they're likely sitting in cache the entire time that the tests are running. So, and to that point, even as relative comparisons, there are some limitations with how well these benchmarks hold up. The biggest challenge that I've found with the test is setting up good input data. If your class uses internal state or data structures, conditional statements, you're gonna want to have some variations in the input so that you're testing all the code paths and you're measuring how things would perform under the best and worst case scenarios, as well as the most likely scenario. You're generally going to want to optimize for the most likely scenario, since that's what happens most often when your code runs. So what about performance at the macro level, or if you need to troubleshoot performance of your application? The Java Flight Recorder is a great tool for that. It's very feature rich. You can have it run along with your application in production. You can set it up with JVM parameters and configuration, and it'll gather data for you, and then you can analyze that data on your dev box later down the road. So this tool can tell you things like if there's a thread that's blocked and what it's blocked on. It can tell you if there's another program stealing CPU cycles from your program. It can tell you when and where memory is allocated. But one of the primary things that I've used it for is looking at the call tree. That along with the hot methods tab can show you which methods the CPU has spent the most time in. So you can even drill down into the call stack from there and identify all the places that those methods were called. So even with that information, identifying performance issues, it takes some work, and you're going to spend some time doing the investigation. Just because an application is spending a lot of time in a method doesn't mean that time isn't justified. So you can't expect to just go into this tool and look at the top of that call tree and say, oh, there's my problem, because the function that it's spending time in may be a very well optimized function. So it takes some investigation to find the useful bits. And because it can be time consuming to use, I generally will prefer instrumentation messages if they can give me enough information to make a proper diagnosis. So when I say instrumentation, what I mean is, like, in production, you have messages that are being output in some form, like metrics, or even if you're just logging it, to be able to see things like memory usage, or the time that an event entered the system to the time that the event exited the system, and maybe some places in between for some milestones. So that way you can start to get a sense of, which pieces of the system are taking the most time. Also remember that you're going to get the best insights if you're running this application on production-like hardware with production data. Otherwise, you're not really guaranteed that the application is going to perform the same. So when an application is running slow, it's kind of our knee-jerk reaction to upgrade the hardware or suggest upgrading the hardware. And a good example of this is when database performance is suffering, and really the real issue is that we wrote some terribly unoptimized query. And in that case, uplifting the database hardware isn't likely to do much, if anything. So don't skip to a solution without a proper diagnosis, or else you could waste a lot of time or money. Or maybe you'll save yourself a lot of time and money because you got lucky and it actually was a hardware problem. But always identify the constraint first. Just don't, the idea is that we don't want to jump to conclusions about what the performance issue is. So high memory usage. A lot of times, people will look at top, they'll see high memory usage, they'll see high CPU usage or other resources running hot, and they'll use that as like a justification that this hardware isn't performing well. But high memory usage really doesn't impact performance unless the usage is so high that you start dipping in the swap space. And high memory usage could also be correlated with cache coherency issues. But I wouldn't jump to that conclusion either. I would look at the cache miss statistics to determine that. So, if you're seeing high memory, look at your swap usage, look at your cache misses, and if those are in a concerning range, then considering upgrading the hardware makes sense. Likewise, high CPU usage doesn't mean that there's a problem. It's expected that you're going to have high CPU usage if your application is constantly doing work. You might see some gains by upgrading a CPU to a CPU with a higher clock speed, but I think you could pretty much make that blanket statement for anything. Adding CPUs is usually what we go for. Like, oh, let's throw it on a machine that has more CPUs, but that's really not going to help the issue unless you have more threads than you have CPUs. And those threads are active all at the same time. Otherwise, if maybe you have a multi-threaded application, but they're not doing work at the same time, or maybe there's only like one of those threads that's actually critical and the bottleneck of the application. And if that's the case, then you may consider something like using task set or NUMA control to bind that critical thread to a CPU core and disable IRQs on that core. So, that's something that you can do without a hardware upgrade. So I also wanted to mention that, I realized in my abstract for this talk, I had mentioned that a lot of times performance concerns are addressed with MapReduce or a computing cluster. And so I wanted to take a minute and speak to those solutions as well. Using MapReduce and using a cluster are great ways to improve your throughput. You're going to find a lot of the things that I'm going to talk about tonight are related more to latency than throughput, because that's latency is usually what we're focused on in trading. So the big difference between latency and throughput is if you think about cars on the highway. Latency would be how fast the car can drive, and throughput would be, how many cars can, get from one exit to another in a certain amount of time. And you can increase throughput by adding lanes to the highway, just like you would add computers to a cluster. But if you want to improve the speed that a single car can drive, then you need to be focused on some of these other techniques that I'm going to share with you tonight.
Hey James.
Yes.
Do you want me to hold questions until the end, or do you want to take them as they come?
If you don't mind, I'd hold them because I kind of have to juggle a few different screens here.
Okay, sure.
Which
Yep, no problem.
Annoying to juggle them. So yeah,
all right.
Absolutely. Thank you. So I can't wait to see what the questions are. So now actually the anticipation here is killing me. But anyway, we'll talk a lot more about latency tonight than we will throughput. There's nothing wrong with map reducing or computing clusters, but I feel like most people, when they're thinking about latency, that's where their mind is. Or when they're thinking about a performance problem, they're automatically thinking throughput, where I want to show that those two things are separate concepts. So if you're going to put in all this, you put in all this effort to write this high performance code yourself, it's also worth considering high performance libraries. While there's alternatives for almost every standard Java library out there, I figured collections libraries are something that most of us are using. So maybe this is a universal suggestion that if you feel that your application your application speed could be improved by speeding up your collections, then this slide's for you. I just went onto the internet and kind of grabbed a smattering of collection libraries that all boast of high performance and low memory footprints. Some of them minimize garbage, and some of them have specialized implementations for primitives. So you don't have to do all the work yourself. There are libraries out there, some that are open source or at least free, and you might get some performance gains from them. So I want to talk a little bit more about the specialized implementations for primitives, but first, I I realize most people probably know what a primitive is, but just want to kind of touch on that. You know, the primitive is int with the lowercase int. Integer is an object that wraps an int. So the primitive data types are recognizable in that they have that lowercase first letter. Primitives are faster than the object equivalent. For how much faster? Well, on the slide, you'll see some results here from a benchmark test that iterates through an array of integers and does an equality check with a number that's passed in. I don't know. It was all I could think of for a performance test, but I just wanted to have something that some empirical evidence that these primitives are actually faster than their object equivalents. And I figured the equality operation is probably the fastest, most straightforward operation that you could do with an integer, and we can still see that at the 50th and 90th percentiles, the array of primitives was twice as fast as the array of integers. In practice, the equality operation of integers is probably even slower than that. Remember, in the benchmark tests, these objects are likely to never leave the cache. So if they never leave the cache, they never needed to be loaded from memory. And getting things from memory is a much slower operation than getting them from cache. With an array of primitives, you also have these values that are stored in contiguous memory addresses. With an array of objects, the elements are references to memory addresses where the object is stored. So you're having to go out and kind of pluck these objects from memory. Then once you have the objects, you're making function calls to retrieve the primitive values that they're wrapping. And so you're doing all that extra work, really, where when you have a primitive, it's stored on the stack rather than the heap, so it's much faster to access. Another characteristic of these wrapper classes is that they're immutable, meaning that once they're assigned a value, if you assign them a new value, the old object will become garbage, and a new object will be made and the old object will become garbage. So you have an allocation and a deallocation happening unless there's some, unless the compiler figures out some escape analysis logic to optimize that out. But I don't think that we can bank on that. So why does the integer class even exist then? Its main purpose is actually to be compatible with generics. Maybe most notably for all of us, the collections class. So, it's easy to use a collection of integers and not realize that it's causing these performance compromises. And that's in part due to autoboxing. So when you pass a primitive into a collection, the compiler is automatically converting that primitive into its object equivalent. That's called autoboxing. Likewise, when you assign a wrapper class's value to a primitive, the compiler automatically unboxes it. So here we have some examples of how you'd write the code to take advantage of autoboxing, and then how the compiler is going to interpret it. Autoboxing and unboxing basically occurs anytime there's an assignment or a function call in which the value is a primitive and an object and the object equivalent was expected, or vice versa. So autoboxing, it's intended to make life easier for developers, allowing them to use the primitives and the object equivalents interchangeably. If you were working with an old version of Java, you were expected to write all this boilerplate code yourself. So it's nice to have autoboxing, but there is a performance cost associated with it. So it's useful to be aware of when it occurs. So now let's look at the performance costs. Here I've tested a standard collection versus a specialized collection that avoids autoboxing. So this specialized collection implementation, it's not using generics. It's an implementation that is specifically using ints, using primitive ints. So it's not, these specialized implementations, there's more code to write because you're not able to take advantage of the generics, else you have your autoboxing problem. But again, somebody's already written this, so if you feel that this would, using this specialized implementation would be beneficial to your program's performance, it's available to you. This function here basically takes in an array of ints and returns a map of numbers and how many times that number occurred in the array. The specialized implementation was about 3 times faster, and the variance between the two implementations is about the same. So also remember that there's a cache effect here, meaning that the standard collections performance would be worse in an actual application because the objects may not have stayed in cache. Another big gap here is the effect that autoboxing has on garbage collection. The line in the standard implementation that's adding 1 to the frequency is essentially throwing away an object each time it runs. So you're creating one object becomes garbage for every iteration of this loop. Again, the compiler has some escape analysis that it does that it might be able to recognize some inefficiencies like this and optimize them out. But I wouldn't rely on that. I'm not an expert on it, but from what I've learned about it through the research that I've done, it only works in some kind of like straightforward use cases. And if your code isn't all that straightforward, if all the autoboxing isn't happening within just one function, it may not recognize it. So, for these reasons, garbage tends to accumulate over time. It seems benign at first, but the next thing you know, you kind of have this just landfill of objects that need to be discarded. Automatic garbage collection, it leads us to overlooking the cost of creating and cleaning objects. We're more apt to create objects that have a finite life and just not think about it. Garbage collection is a feature that not every programming language has. In C++, you're in charge of deleting what you create, and mistakes by developers can cause memory leaks. So, garbage collection saves us from that. But the price that we pay is that there can be pauses during execution that happen at inopportune times. So basically, when Eden space fills up, that's when garbage collection starts. The garbage collection settings can be tuned via the JVM parameters, including the type of garbage collector that you're going to run. Some are going to do work more quick. Some are going to pause the application and work more quickly. Others are going to minimize pauses and take longer. You can also tune Eden space to be smaller. That will make garbage collection faster, but it's going to happen more frequently. You could tenure objects earlier to get them out of Eden in fewer GC cycles. But that's going to mean more objects will be persisted in the old generation. So there's a lot of trade-offs here, and you have to decide what's best for your application. But the best strategy is to prevent GC from being triggered at all. Ideally, all memory would be allocated when an application starts up so that it's out of the critical path. Anytime that you're allocating memory, you have a new object in Eden space. And again, when Eden space fills up, garbage collection will start, even if there's no garbage to collect. The Eden space filling is the trigger. So when we know that we're going to need a lot of instances of a class throughout the course of running an application, object pools can be used to create a whole bunch of those instances in advance. Pools are great for transient objects because rather than allocating and deallocating, we can take an instance out of the pool, use it, and then put it back into the pool. So rather than subject you to the dry diagrams that I had come up with. I found this diagram on Medium, and I thought it was a pretty good representation of what happens. So you have something that needs an instance of an object. You check if there is a free object available in the pool. If not, you create it as per usual, and then you use the object. And when you're done, you either way you release it back to the pool, and that way other things can pick it up and use it. So, ideally we've sized these pools so that we never need to create an object on the fly. That way we're never triggering garbage collection, and we can get some feedback on how good of job we've done doing that. If we have our application, if we add some instrumentation for a high water mark of the pools, and then we can use that feedback to size our pools correctly in our configuration in the future. Strings are an object type that aren't a good candidate for a pool. They're immutable, so their value can't be changed after they're created. And for that reason, they're also a big contributor to garbage. There are alternatives that are mutable, like character buffers or character arrays that you could pool. Character buffers probably more appropriately, because otherwise, how large of character array are you going to make? But buffers are often used when reading data from files or sockets. So you might even be able to access those characters directly from the buffers that you're using for those reads without actually copying the content. So, there are some workarounds here, but either way, strings and buffers, character arrays, they're often involved in expensive operations. For instance, here's the Java's string equals method. And in the worst case, you can see that it's requiring comparison of every character in the string. So that's as opposed to a primitive value where you can compare primitive values with a single machine instruction. You're having to go through an entire loop. So minimize the use of those data types if you can, and if you can, consider something like I talked about with the fixed messages, where the exchanges are giving us a mapping of integers to string values to use throughout the day, or if that's not in the cards, if you have customer ID, account ID, something akin to that, it may just be more efficient than passing around a string. So throughout this talk, I've mentioned Hotpath and CacheFX a few times. So I wanted to elaborate a little bit on how that works. I'm not an expert in this area, but there's a lot going on. The JVM, the OS, the CPU, they're all involved in making speed optimizations. And as the code runs, they're finding an optimal code path, referred to as the hot path, and that's going to include instructions as well as objects. So it may include the just-in-time compiler compiling instructions, and caching and objects and instructions as well. And it also does something called branch prediction, where for conditionals, there's predictions made about which branch would be used. That's done because the CPU works faster than we can load from memory. So we try to load as much in advance as we possibly can. The downside is that when there's a incorrect prediction, we're stuck waiting for instructions from the alternative branch to be loaded, referred to as a cache miss, that you didn't have the instructions that you were looking for in cache. So there are the more alternatives that a conditional statement has, and the more evenly weighted the possible outcomes are, the more performance is going to suffer, and it may even make branch prediction ineffective, or the CPU may just skip it altogether. Likewise, inline caching occurs for virtual method calls when there's multiple implementations to choose from. So there's an attempt to predict which concrete implementation will be used so that the instructions for that class can be loaded in advance. When there's only one concrete implementation, the cost of the virtual call is essentially optimized out. But if there's many concrete implementations at the same call site, then that call site will enter what's called a megamorphic state, in which the prediction suffers quite a bit, performance suffers. I really made it a point to use that vocabulary term, megamorphic state. Someone used that in an email to me one time, and I was just, since then I've been trying to work it into a conversation. It just doesn't come up as often as I'd like. In my experience, it's really hard to gauge how caching and runtime optimizations are going to affect performance, but there's a lot of these optimizations and nuances I'm still learning about. I actually just learned about one today in which if a switch statement is using enums, it will generate an anonymous class under the hood. So I'm kind of keen to do some more reading about that this weekend and see what the implications are and the exact details of exactly when it may or may not occur. In my opinion, having a combination of learning the academic answers and running some of the performance tests, like I showed earlier in the presentation, is really useful in making the right choice. I wouldn't rely on experience or academia solely. So just to recap, when should you be thinking about performance? You should be thinking about it every step throughout the system development life cycles. So, starting with your architecture, what are the performance goals of your architecture? What is your system going to do? Try to figure out how you can achieve that. When you're writing your algos, you want to consider performance. Big O time makes a big difference. When you're structuring your messages and your data, how will those impact your algorithms? When you're choosing libraries that you're going to use, are there third-party libraries that could help you here? When you're managing your objects, could you rely on some object pools? Are you using types that are immutable and could create garbage? Well, I guess I just said it. And choosing your data types. I haven't used a primitives wrapper class in years, and it really hasn't cost me any measurable time in development to make that optimization. So, I encourage you guys to think about the same. Then we get in the testing and monitoring performance, and you really don't want to wait to look at performance till you get to that stage, or else you could be telling your boss that your system needs a full redesign. So in close, just like to encourage everybody to stay curious, continue to read, run experiments, and hopefully share what you've learned like I have at this UJUG talk. I hope to see some of you giving presentations in the future. If any of this was intriguing to you, consider coming to work with us. All experience levels are welcome. You can apply right on Goldman's website or email our recruiter. You could send me a message through LinkedIn or through Meetup, and if you prefer, and we can have a quick chat. But with that, I thank everybody for your time tonight.
Alrighty. Thank you very much. Thanks, James. So I think we will move on to questions. And currently we have 4 on there. If other people have questions, please use the ask a question down there in the bottom, and we will get to those. Currently there's one upvoted. Are you looking at those, James, or should I read them myself?
I think I'm looking at it. What tools, hardware is used for the command bus?
Yep, that would be the first one.
Okay, yeah, great question. So, there's a lot of different implementations that you can use for a message bus. For ours, we've chosen the multicast communication pattern. So in trading, multicast is used quite a bit. It's similar to unicast in that there's no ACK like there would in TCP. So there is the possibility of dropping messages, but the reason that it scales really well is that you're not asking you're not having to send the message individually to each of the consumers. The application can publish the message, and then consumers basically send a message to the switch that says, I want to subscribe to this multicast channel. And then the switch communicates with other switches, and so that there's the kind of subscriptions that make their way all the way through the network. And anytime that there's a message published on that bus, it'll make its way to all consumers. So it really doesn't involve any specialized tools or frameworks or anything like that. This is something that you could. I mean, there are things like 29 West is a company that provides a multicast message bus solution with some bells and whistles on top of it. Like, for instance, like they give you like a yellow page catalog. I can't remember what they call it, but it's like a service where you can look up what the addresses are for any of the multicast channels throughout your system. But you can be very bare bones about it as well, and just write your own socket that's publishing a multicast packet, and likewise write a socket that receives multicast data. Okay, second one here. Can you please explain against the difference between latency versus throughput? An example. So latency and throughput. So yeah, the cars one is the best example I have. Like it's speed versus it's how fast one thing can get done versus how many things can I get done in X amount of time. So to say it a different way, imagine that, like, if you have a funnel, right? You're pouring all this. I don't know if this is a good analogy, but I'm shooting from the hip here. You're pouring something into a funnel, maybe a bunch of little beads or something. I don't know. So each one of those is representing an event, and the bigger that your funnel is, the more events that you're able to process at a given time. So when you're adding additional machines, you're essentially making that pipe larger and larger, right? But the events that are going through that pipe, they're still going at the same speed. It's not like they're that you're processing events faster. You're just processing more events in parallel. So if you have in trading, we often have pipelines where we have things that need to be done in sequential order, events that need to be processed sequentially. So, to process that event, we have to do, step 1, step 2, step 3. We can't parallelize it into doing 1, 2, and 3 at the same time. And so our latency is, how long it takes for that event to be processed beginning to end. Our throughput would be if we added, maybe we add a couple machines and we're able to, split, have multiple events processed at the same time. So then our throughput would be increased, but our latency would not. So the next one, in the deterministic, event-driven, eventually consistent architectural slide you mentioned, how do you guys handle situations where you need immediate consistency related to auth Z? So let's see. I don't quite. I don't have a great answer to that question because of my lack of working with authorization protocols. But I guess what I would say about that is the system. I don't know that the system is eventually consistent. I would say that it is almost immediately consistent. If in theory, if every one of those applications can keep up, then they're all consuming the same message at almost the same time. So if there was a request, I'm just visualizing how I would handle this, but if there was a request for access or something, I'm envisioning that one application is raising the request, and that event gets sequenced by this special event sequencing application, and put onto that event stream. That event stream is where the other applications are reading from. Maybe one of those applications is a authorization app. So if it chooses to authorize, then it would put its user authorized command on the command bus, and the event would be again read by the event sequencer. And if the event sequencer is okay with that, it will put it on the event stream, and then all the applications will see that the authorization was successful. If there was a secondary application that was also trying to authorize in tandem, the event sequencer can handle that. You can build in, preferably as little logic as possible, but you can build in logic to that, event sequencer to say, to reject things, to say, oh, well, I see a duplicate authorization, that authorization request has already been fulfilled. So, just discard any, any other commands that attempt to accept or reject the authorization. So, it's the same thing here with the Exchange's matching engine. It has to, the matching engine has to have a certain amount of logic baked into it, because it has to be the single point of decision making. So for those single points of decision making, having them in a single place like the event sequencer or another single app would be the way to do it if you can, in my opinion. What type of objects do you keep in an object pool? Custom objects? How do you clear object state before reusing? Yeah, good question. I would say custom objects. I don't know that there's, the strings and all the wrapper classes for the primitives. They're all immutable, so they're not good candidates for putting in a pool. So from that definition, I mean. In the code that I'm working in, the majority of the code there is written in-house. If I were dealing with a third-party application, I may, if it's something that I wanted to pool, I may consider wrapping the object type with a custom class. And when you wrap it, you can add, as you suggested, an initialize method and cleanup method. Those are useful so that, if you're taking something, it's not required necessarily, but, if you're taking something out of the pool, you for objects that maintain state, you want a way to be able to reset that internal state. So if you can have an interface for init and cleanup for a poolable object, I think that makes sense.
Do you mind if I add something to this, James?
Sure, yeah, absolutely.
I've not worked on low latency systems like James has, but this is definitely one of those things where you don't want to try and outsmart the JVM. because the JVM is very smart at what it does as far as object creation and whatnot. And definitely you'll want to profile your application before you actually go down this rabbit hole of, do I need to create a pool? How big does the pool need to be? All of that kind of stuff. But if you're in doubt, just let the JVM handle its thing and then test it and figure out whether or not you actually need to go down this hole, because JVM is very good at what it does, and it has been doing it for quite some time.
What do you think about streams and pipes with regards to performance? Streams and pipes. I think I maybe need some elaboration there. Yeah.
If I might venture a guess here on this one, they're probably talking about Java 8 streams and the Lambda express engine and whatnot that you're able to do with
gotcha.
that.
Yeah. Yeah, that's one of those areas that where I'm not quite sure of the performance there. That there are definitely some optimizations that the just-in-time compiler makes that where the stream performance may be optimized, but I will say this: lambdas tend to generate garbage. So I've observed that, not specifically with using streams, but I think it's something to test and read more about. I'm not quite sure.
Streams typically are done on the same thread unless you end up doing a parallel stream, which uses the fork join thread pool in the JVM, which is default to I don't remember what it is, but it's not a very large pool, and it's something you have to tune at JVM startup if you're looking to do a lot of parallelization with your streams. So that is definitely something to take a look at if you're looking for performance with a streaming API.
All right, this talk's great. Even I'm learning stuff here, so learning stuff from my own talk. A bit OT. What role does ZI and MI have at GS? ZI?
Yeah, that's a good question. I'm not sure what at least half of the acronyms in this question mean. But Jan, if you can further clarify the question, that would be very helpful on that one. Also, if there are other questions while Jan's working on that one, or if anyone has other comments they would like to talk about real quick, we can field questions for at least another good 10 minutes or so.
Yeah, I'm also happy to hear about anybody else's experience with Java performance. There's a lot that I don't know. So,
all right. So we've got a comment here from Jan. He says 0 intelligence for ZI and MI is minimal intelligence.
Oh, you know what? I guess I'm pretty green to those terms. I'm not sure what role artificial intelligence in general plays at GS. They're not technologies that I've worked with in my department. There are some teams that do machine learning for risk analysis and trading strategies, if I'm not mistaken. But yeah, it's a big organization. So, but you know what? If you hit me up on send me a message on meetup.com, I'd be happy to find those answers. And yeah, let's find out for you. Yeah, if there's any questions at all about roles at GS, definitely send me a message or send our recruiter a message, and that we're always happy to answer that. We're always looking for talented people.
Very good. I added one that I was actually curious about, and this might really depend on which JVM you're using. But in your slides, you had benchmarked some of the other garbage collectors that are there. Have you guys taken a look at G1 or Shenandoah, or some of the other garbage collections that are out there?
Yeah, G1, yes. Shenandoah, I'm not familiar with, but
Shenandoah is done by Red Hat. You can find it in the Open JDK ICE in, I think, Java 8 and above.
Okay. Yeah. We actually, I think that was on the garbage collection slide. I actually have not performance tested the garbage collectors. We have tuned our garbage collection, which I'm aware of some of that. I'm not, but I wasn't involved in the process, so. I don't know. I don't know which of the collectors that we use specifically, actually.
No worries. So we've got one for your Twitter handle, and as well as stating that verbally, would you mind adding a comment on there so people can just copy and paste if they need to?
I have no Twitter handle. What Java versions of JVM vendors do you use? We're using Java 8. Not sure of the JVM vendor. I'm actually I was reading about Java 9. I'm kind of excited to migrate to Java 9 because there's the ahead of time compiler. So curious what that can do for us. Are GS systems mostly in physical servers, virtualized versus cloud? Yeah, I'd say we use virtualization for most things, and I would call it the cloud. So we actually have some AWS servers too, but we also have GS data centers with with servers that are a lot of them that are running hypervisors, running VMs. And yeah, I would consider it a cloud environment for the most part. And we have all that is managed at the enterprise level. So it's pretty efficient, really, like to spin up a new server takes, it's just as easy as getting an AWS server. It's, you pick what you want and you make it, and it's next thing you know, it's there for you. We also have a thing that we also have a thing called the data lake. I guess I'll just mention because I went to a talk about the data lake maybe a year or two ago, and I thought that was pretty interesting. So it's kind of GS's. I don't want to call it a neural network, but all the data that we have is available in this lake that you can pull from. So teams that are either they're mining data, or it can help prevent data from being redundant. But yeah, I mean you could use it for mining for relationships and things like that. So it is a pretty interesting unique feature that GS has. Do you run your own data center, or do you run on cloud vendors or some mix? It's a mix. So specifically for the department that I'm in, when we're talking about trading, we have data centers with some of our less performance critical pieces, and then we have our performance critical bits stored in a co-location in a data center that's co-located with the exchanges. So that way, like all these different trading companies, they all have different cages with their servers in them, and there's a cage for the exchange, and there's wires run from everybody's cage to the exchange. So that's one of the instances that I know of that in which we're using something other than a GS location. But like I said, we also have some AWS servers for, my team stores historical logs on an AWS server. Cheap and easy to use. Are there any articles that you refer or you review Java specifications? I feel like for me, I often kind of my learning is very ad hoc. So if I'm working on something and I'm interested in a topic, or maybe somebody brings something up, or a coworker mentions how a feature or a term that I'm unfamiliar with, I'll go out and I'll read about it online. Of course, I've got my fair share of books on Java as well, but the only one that I've read for performance really went so far deep in the JVM, it was just gobbledygook to me. And I don't tune. I work with a couple other 100 engineers on this trading system, so I'm not tuning the JVM. So it just got into an area that is like, where you can't know everything, or if you learn a lot of things that you never utilize, that knowledge just kind of falls out of your head.
Very good. I'll give it just a couple more minutes to see if we have any questions.
Sure.
But Madeline or Soraya, if one of you are still on and wouldn't mind talking about the swag that Goldman has to give out, let me know and I'll bring you up on screen real quick and we can discuss that. Oh, cool. Madeline's still on. All right. So I'm going to invite her up real quick so that we can talk about the swag, and we'll get going with that in just a little bit. All right. So let's see if she comes online. There we go, Madeline.
Hi there. Okay, so as I mentioned earlier, we've got two pieces of swag. One is a Goldman Sachs hoodie. We have those available in a medium and a large. And then the other one is a small portable Bluetooth speaker that also acts as a phone charger. Are you able to pull two people from the audience randomly to select those who get prizes?
Yes, I am. I have those, and we will get to those in just a minute. If we don't have any other questions, I will go ahead and do the door prize drawing. But that should work. And just for those that are interested, or if you need to know, Madeline, do they need to be local to the Utah area for those?
Nope, don't need to be local. So wherever you are, we'll get it to you.
Excellent, very good. All right, I'm not sure which one of you two want to take this one, but there is a question over here. At Goldman, do engineers work with algorithm development staff? This is by Jen.
So I actually think I know the answer to this one. So yeah, there are some algo teams that that consists of engineers, and so they're algorithms that are on the fairly beaten path, and engineers implement those and are in charge of them. There's other teams there's other strat teams that are still under engineering that come up with strategies for various things. Like in one of the teams that I used to sit next to, if I recall, they were coming up with a strategy for trading baskets of currencies in the most optimal way. So somebody says, I have all these currencies that I need to trade in and out of, and I need to execute these legs all at the same time. And they've come up with a way to work those orders. So they are engineers that also kind of have a background in mathematics or like research scientists, strat teams. Yeah.
All right, very good. So I have the door prize drawings up here. So let's come over here, share screen. Let's share this one over here. Hopefully that shows up. Oh, it's there. So what we've got going on tonight, the JetBrains license is going out to Mark Smith. Mark, let us, well, you don't have to let us know, but that is available to any of the IDs that JetBrains has. Same goes out to David Marsh, who also won one as well. Adam, I will get you the code for the Agile Learner subscription over there. And Raj, I'm assuming you're interested in cookies. If you are, just let me know over there in the comments, and I will get your information out over to Kate from Tech Systems. And let's see. Yes, cookies. Very good. And then, of course, Zen and Scott, Zen Fairbanks and Scott Greenman, you two are up for the swag from Goldman Sachs. And Madeline, I'll let you figure out how you want to distribute that or whatnot. I will give you email addresses. Does that work for you?
Yeah, that's perfect.
Perfect. Excellent. Very good. All right. Thank you, everyone, for attending. We appreciate it. And we look forward to seeing you again next month.
Thanks all.